Good morning, good afternoon, good evening, whichever is applicable to you. Welcome to part C of chapter 7, Thermochemistry. This is the last section I will cover in chapter 7. Please have a pen and a paper. I'll be working some examples which you will need in order to complete module 7 in Alex and as well as in studying for the quiz and exam. This is going to be a short session. It will cover section 7.8, 7.9, and 7.10. Real quick before we look at 7.8, in the last part P, we look at thermochemical equation. Recall in part P, thermochemical equation look like this. This is just a generic A plus maybe 2B going to C with change in enthalpy for the reaction given in there, maybe just some numbers, maybe positive 58 kilojoules. And when you look at this, kilojoules means per mole, which means when 1 mole react with 2 moles of B, this is the amount of energy we need. This is endothermic. If it is positive, we say endothermic reaction. We learned in the previous section that enthalpy of reaction or heat of reaction is extensive, which means it depends on the amount of reagents in a chemical equation. In part C, section 7.8, we will look at the manipulation of chemical or thermochemical equation and the relationship involving the change in enthalpy of a reaction. In section 7.9, we will look at how to determine the enthalpies or heat of reaction from the standard enthalpies of formation. There are some literature values which you will need, or you will be given for that in order to calculate the standard enthalpies for chemical reaction. And lastly, briefly, we look at the use of energy in section 7.10. So let's look at the relationship, 7.8, relationship involving enthalpy of reaction. There are 3 relationships when a thermochemical equation is multiplied by a factor, all right? We multiply the enthalpy for reaction by that factor as well. If you look at the first equation in here, let me just blow up this, you're gonna see, well, this is the thermochemical equation. It is exothermic, it gives away or it releases energy 393.5 kilojoules for the first reaction here. If we multiply by a factor, in this case, we multiply the first reaction by 2, you'll also multiply the enthalpy for reaction by 2. That's where 787.0 kilojoule is obtained. So remember, multiplying a thermochemical equation by a factor, you also need to multiply the enthalpy for reaction by that factor. It's extensive. We define extensive, intensive property at the beginning of the semester. Extensive property depend on the amount of matter present. So here, if we multiply by 3, we multiply by 3. If we multiply by 4, we multiply by 4, and so forth. So remember multiplication. The other manipulation of thermochemical equation is if we reverse the thermochemical equation, the sign of enthalpy for reaction will also change. This is the thermochemical equation. If we flip, like change the equation, the sign also will change. We will be using this down the line, remember that. So there are 2 manipulations we have looked at so far, multiplying by a factor and reversing the equation, Thirdly is if a reaction can be expressed as a series of steps, then the overall enthalpy for reaction is the sum of, sum of heat of reaction for each step. Hypothetically, A reacting with 2 moles of B, 1 mole of A reacting with 2 moles of B to form C. This is the first enthalpy of reaction, and assuming that C decomposes to produce 2 moles of D, we can determine the overall enthalpy for reaction by just adding enthalpy for reaction 1, enthalpy for reaction 2, to get the enthalpy for overall reaction. So if there are series of thermochemical equations, you have to look at how the equations have been manipulated to calculate the overall reaction. We call this Hess's law, all right? I know you're wondering what is Hess's. It's the name of a person who came up or proposed this approach, and the definition for that is the definition of Hess's law states that if a process can be expressed as the sum of 2 or more steps, if a process can be expressed as the sum, underline the word sum, of 2 or more steps, then the enthalpy change here, this enthalpy change right here is simply this enthalpy change equals change. This is change in enthalpy, of a reaction like that. So we can find the overall enthalpy for the reaction as a function of the sum of enthalpy values for each step. So this is step 1, this is step 2. We can find the overall by finding the change in the overall reaction. Some others call this, we call this sometimes also, this Hess's law is called Hess's law of heat of summation from the word sum. When you find the sum of 2, you are adding. So Hess's law is sometimes called the Hess's law of heat of summation. We look at momentarily, it is also a manifestation of a state function. Remember how we define state function doesn't depend on how we cut to that state, but it's just determined by the initial and the final, change of enthalpy in a chemical reaction is the same regardless of whether the reaction takes place in one step or several steps. Remember the altitude of the mountain? There was an analogy of, scaling the hill to the peak of 10,000 feet. Route A, you had to meander. Route B, you had just only to go straight, which was 5 miles versus 12 miles, regardless of which route you take, all right? Still the altitude remained 10,000 feet above sea level. Likewise, in Hess's law, doesn't really matter how many steps. We can have several steps here before we get to the final, but still the overall heat of summation will be the same regardless of how many steps we take in that. Okay, so that is a manifestation of state function in Hess's law. So in summary, these are the 3 manipulations you need to remember. Please watch this YouTube video on Hess's law. It will enhance your understanding of the law. There will be some calculation which you need to be well-rounded. Let's see an example on Hess's law or one of the manipulation. Let's see. the manipulation. And remember, manipulation cannot be only one. You can have three manipulations at the same time. For example, this is a thermochemical equation where 2 moles of A combine with 1 mole of B to form 1 mole of C with an enthalpy of reaction given as 122 joules, all right, joules per mole. The question is, what is the reaction for, or what is the enthalpy for change in enthalpy for the reaction 2C breaking down to 4 moles of A plus 2 moles of B? You have to ask yourself, what is the relationship between what you are, the equation you are looking for, its change in enthalpy for the reaction with the thermochemical equation? It could be 3 thermochemical equations, but you are given the overall. So when I look at this, C has been multiplied by 2, and then the equation has been reversed. So it doesn't really matter whether you multiply by 2 and then you reverse, or you reverse and then you multiply by 2, you still arrive at the same conclusion. Remember, state function. Doesn't really matter how you do it. So if we reverse first, if we flip the equation, that means the sign will change to be negative 2. So if I do this, let's just have here next, if I flip the equation, it's going to be C. Look at what's going on here. So it's going to be C going to 2A plus B, and the enthalpy for reaction for this Rxn will be now negative 122 kilojoules, 122 negative, because we flipped the equations. One of the relationships we looked at. And then we need to multiply pi 2. So if I multiply pi 2 here, all right, so I'm just going to say here you multiply everything times 2. So this is going to be 2C going to 4A plus 2B. And the level for reaction for this is negative 244 kilojoules. Please be careful, because sometimes some people might just try to guess in the sense that there are two values. The only difference is the sign. So C and D, they have the same numerical value, but the sign is changing. Be careful with that. The correct answer for this is D. So this is what we are looking for. So there were two manipulations, flipping and multiplying by a factor. You reverse and then multiply by a factor. There is another conceptual question here. What effect do these changes have on change in enthalpy for the reaction? Multiplying by a coefficient of 2. We just saw it here that multiplying by 2 will double. So the correct answer here is the value for change in enthalpy will double. See how this double? If we divide by 2, this is going to be 1/2 by that. So I just defined this previously. You should be able to define Hess's law. Sometimes it's hard to determine the enthalpy for reaction, but we can use calculated or published at the end or at the back of the text. There are published values for change in enthalpy. For reaction, you can use that, right, to perform the calculation. We looked at the state function before, just like change in internal energy for the system. Enthalpy for reaction is also a state function. Doesn't really matter how many steps we take. That's all about Hess's law. You need to know that. Let's see an example here on Hess's law. It's the same as what we just looked at, using Hess's law with 3 equations to calculate the overall change in enthalpy for the reaction. So here are the few, you may not see that. Let's see if I can fix this so that you look at it. I'm just going to have the overall reaction here. Yes, so here is for each reaction, you need to look at how the equation has been found. Simply, this is the overall. Even though we don't have here the values, I will give it to you, but let's see how the three equations have been manipulated. If I look at ethylene, this is ethylene, it is on the product side in the overall, but it is on the reactant side on one of the thermochemical equations. So it means we need to flip, all right? We need to flip equation 1. That means the sign of a change in enthalpy for reaction 1 will also change. The sign will change because of flipping. If I look at the carbon here, carbon is still on the reactant side, so it means it's going to be on the reactant side, but it needs to be multiplied by 2. So you're going to multiply by 2 the change in enthalpy for equation 2, and the hydrogen gas is on the reactant side, so thermochemical equation 3 will remain the same. We are missing the arrow here. Gas is coming from here. We forget to have that. So in overall, this is the solution. All right. When we multiply by 2, we just also multiply by 2. That, remember, you cancel out the values. So half oxygen, you divide by 2. There was 1/2 here. You see this? If you divide by 2, so that why do we have to divide by 2? All right, we need to divide by 2 based on the number of oxygen we have in there, so that oxygen and oxygen will go away 5-2. And the overall, adding everything here, this is what you get for the overall reaction, So remember, when the equations are added, there are two carbon hydrogen on both sides of the arrow. We need to cancel. You'll have to cancel those two in the overall. Here is another example we can look at. Hess's law, we'll have to figure out how the overall equation has been obtained from the three thermochemical equation, equation 1, equation 2, equation 3. We are asked to calculate the change in enthalpy for the reaction of ethylene. This is ethylene with fluorine gas. So you have to evaluate, study the overall, and ask yourself, how did you end up here? For example, ethylene is on the reactant side, and in one of the thermochemical equation, the third one, it is on the product side. So we need to flip the equation 3, and the sign for enthalpy for reaction for equation 3 will change to negative once you flip this for ethylene to be on the reactant side. Both fluorine gas in thermochemical equation 1 and 2, they are on the reactant side, so we don't need to change. We don't need to flip, because if we flip, that means the fluorine gas will be on the product side in the overall. So the first and the second equation, we don't need to reverse. We need to reverse only the third one. And if I look at hydrogen fluoride here, we are 4 on the product side, and here we have 2, which means we need to multiply equation 1 by 2. All right. If we multiply by 2, All right, if we multiply by 2, this will be 4 HF. So let's see if I multiply by 2 equation 1, all right? If I multiply by 2 equation 1, it's going to be 2H 2 gas plus 2F 2 gas going to 4HF, and the enter level for this is 1074 kilojoules. We multiply by 2. Sorry about that. I just writing, forgetting that you are not seeing the whiteboard. So here I multiply equation 1 by 2. Look like equation 2 needs to be multiplied by 2 as well. We need to multiply by 2 equation 2. So this will be 2C solid plus 4F2 gas going to 2CF, all right. Change in energy level for this is negative 1360, negative 1360 kilojoules, negative 1360 kilojoules. And the equation 3 is reversed, so we will flip the equation. This will be ethylene on the reactant side, gas going to 2C solid plus 2 hydrogen 2 gas, and change in energy for this will be negative 52.4, and this is kilojoules. All right. So now you have to cancel out just the way we cancel the spectator ions in net ionic equation. What is common on either side of the reaction arrow? If I look at the hydrogen here is the same as hydrogen in equation 1, so this will go away, this will go away. If I look at the carbon as well, this will go away, and this will go away. So we just gonna cancel this, cancel this. What else do we have? What else do we need to cancel out? It seems like there is no other, so we'll be right. Well, the reaction is 1 plus 2 plus H3 for the overall. For equation 1, equation 2, and equation 3, so that we have the overall equation as ethylene reacting with. Remember, this is 2 and 4, adding to 2 gives us 6. You're wondering where is 6 coming from? You add 2 and 4 give us 6 fluorine, 6 moles of fluorine gas to produce 2 carbon fluoride gas plus this CF4. This was CF4 by the way. Two CF4, this gas plus what? Plus 4HF, and this gas, we just adding the 2, and the overall delta level for reaction for this overall envelope for reaction is the sum of everything which is negative 2, 4, 8, 6.4 kilojoules. So we flip the equations, we multiply power factor to get the overall. Please go back again, learn there are worked example in the text. Please look at the worked example and try problem number 83, 85, 86 on page 309 for more practice on SS law and how to find the change in enthalpy for overall reaction. Remember, you may be given the overall enthalpy for reaction, and maybe one of them is missing. You still have to apply algebra and calculate what is missing. Okay. So that is all as far as Hess's law. Let's move on to section 7.9, determining the enthalpies of reaction from the standard enthalpies of reaction. Standard here means the condition is a standard state. All right. Understand what the standard state is. Previously in chapter 6, at the STP, standard temperature pressure, 1 atmosphere at standard condition. Usually the temperature is 225 degrees Celsius or 298 Kelvins at standard. Pressure 1.00 atm. This is pressure. And molarity, the concentration, molarity is 1.00 uppercase M at standard state. We use the subscript node for standard. So if you see this, change in is now different. When we have a subscript there, it means, by the way, this is what I meant by standard state, temperature 298 Kelvin or 25 degrees Celsius, pressure has to be 1 atmosphere, and the molarity or concentration of the reagents must be 1.00 molar. So this is change in, you read this as change in enthalpy of reaction at standard, we call this standard state. Please, this is different from just without the subscript. The superscript here, no subscript, the superscript here means the condition is at standard state, temperature 298, pressure must be 1 atmosphere, and the concentration must be 1 molar. We can calculate or use the standard enthalpy of formation to calculate the standard enthalpy for reaction. And remember, the element must be in their standard state for the formation. We take that the literature values, they are given in the text, and how we're going to use these to calculate for the reaction. These are just the literature values. You may need to refer to this table in the text. You'll be given in the quiz, you'll be given in the exam. When you look at this standard change in standard enthalpy of formation of bromine, and please pay attention to the physical state, because if you look at the gas, liquid, we can also have graphite. Even though we have solid for carbon, is it graphite, is it diamond, or even carbon dioxide? Here, we can have carbon dioxide liquid, carbon dioxide gas. They have different enthalpies of formation. Even liquid H2O and gaseous H2O, they have different enthalpies of formation. We will need these values to calculate the overall enthalpy for formation for the reaction. We're going to be given all this if need be, but you may need to come back here if you'll be attempting end of chapter problems or module 7 in Alex. So for the reaction of element in their standard state for 1 mole of pure compounds, it's just 0. Pure elements, they have their standard enthalpy of formation is given in the Abedex as delta H formation as 0. Remember, this is the standard state. We can now use the standard enthalpy of formation of elements or compound to calculate the standard enthalpy of formation using this equation. And understand that this is the change in enthalpy for reaction at standard state, which means we have to refer to the Abedex to find the standard enthalpy of formation for the product. Remember, this means summation and change in enthalpy for formation for all the products minus for all the reagents. N and N here, these are the coefficient in the balanced equation. You have to multiply, all right, by the coefficient in the balanced equation. And then you just find the difference between the two in order to get the overall standard enthalpy of formation. Here is an example for the thermite reaction we looked before in section 7.1, the thermite reaction for hand warmers. 2 moles of aluminum react with iron 3 oxide to form aluminum oxide plus 2 moles of iron produced. Use the standard enthalpy of formation to find or to determine the enthalpy for reaction. Here, we are looking at this. I forget to put that, but this is what we are looking at, the standard state. So here should be superscript right here. This is not the regular, but superscript here. And by the way, this should be a hint. Use the standard enthalpies. Where am I getting this? You got to look at the Abedex. You don't need to memorize. You'll be given that. I'll give you that in the quiz. So if I'm looking for this, it's going to be enthalpies and then M, enthalpies of formation of the product minus summation, and then N here is the coefficient in the balanced equation, enthalpies of formation for the reactants, R for the reactants. So this is how you set up your equation, product minus reagent, product minus reagent. So if I want to plug in the values, the coefficient here for, so this will be product is 2 times 0 for iron. I'm looking for iron here, 0. If you look at the back of the text, the standard enthalpy for formation for iron is 0, plus aluminum oxide is negative 1,675.27 kilojoules. So you have to find the summation. All right, aluminum oxide. If I go back to that table, let's see how aluminum oxide, not there, aluminum oxide. I'm not sure if we have it here. Maybe I got it from the Abedex, aluminum oxide. So anyway, we multiply by 2 using that equation for aluminum oxide minus for aluminum, it is 0. So here is 2 times 0 for aluminum plus When we multiply by 2, iron 3 oxide, this is negative 824.2. If we multiply that by 2, and the overall here is negative 851.5 kilojoules. This is using the standard state. So I'm just going to look at the standard enthalpy of formation from the Abedex. It's given in the lab, in the text, not the lab. But in the text, there is the standard enthalpy for iron, which is 0. For aluminum oxide, negative 16, 1675.17. So summation for this, 0, you subtract product. This is the product. And these are the reagents based on this equation here, summation based on that equation using the standard state. Please look at page 309, problem 87, 88, and 89 on how to use this equation to find the standard. Remember, standard means there's a superscript here. We're going to use the literature values, in order to calculate the standard enthalpy for reaction. Lastly, let's look at the energy and the environment in section 7.10. It's a brief section on the energy and the environment. Literature states that in the United States, each person uses over 100,000 kilowatt of energy per year. This is a lot. And where is the source of all this energy? It comes mostly from fossil fuel. These are major source of energy, carbon, methane is natural gas. This is octane from octave 8. So octane from the car station 8 carbon-10. Combustion of octane gives energy. These are the amount of energy in kilojoules given by each natural or combustible fossils. Now, there are the belated, amount of energy where it goes 26.2% in transportation, residential, industrial. This is just some of the energy uses in the environment. Energy consumption from different sources, energy consumption by source. Petroleum is taking the lead, renewable energy such as the nuclear reactor, such as the solar power, there is the coal, there's the natural car. On the y-axis, this is quad, and it's quadrillion, all right? It is the British quadrillion, which is the same as, by the way, 1 quad, see that? 1 quadrillion is the same as 1.6, something you may relate to, times 10 raised to 18 joules. It's quite a high number when you talk about the quad. So if you look at 30, if you look at 45, we are talking about multiplying by this to get the actual energy consumption. What I want you to read is make your own notes on probably something you have heard about, the environmental problem associated with the fossil fuel, okay? One, it cannot be replenished. It is estimated that in the next 50 years, maybe natural gas will be depleted, and that is why you see more and more or hybrid cars, 100% electric cars, because of, there is a rush to find an alternative source of energy in case in 50 years we don't have oil, we don't have gasoline. How are we going to move around? It's going to be a disaster. Therefore, there is a need to find an alternative source of energy, in 50 years. The other problem associated with natural or fossil fuel is that there's some additive added to it, which has some side reaction. For example, in complete combustion, release some of the toxic gases into the environment, all right? We will see those momentarily. This is responsible for air pollution. Responsible for acid rain, and of course, the climate change. This is the change in average due to some of the measures which has been taken to mitigate the pollution over the years. There has been reduction in percent sulfur dioxide, which is responsible for sulfuric acid in acid rain, carbon monoxide, nitrogen dioxide, toxic fume, or ozone. This is reduction, which is positive sign that the emission of these toxic gases into the environment over the years has been decreasing to avoid the toxic environment. I don't want to spend more time talking about the climate change. You can read on your own. There is, by the way, a dimensional analysis problem you need to solve regarding the CO2 being released into the atmosphere. And this has been tracking since 1860 to 2020. Atmospheric carbon dioxide is increasing because of the increase in use of fossil fuel, CO2 into the atmosphere, which is responsible for climate change. So in order to reduce the emission of CO2, there has been concerted effort to use renewable energy such as solar, or even electrolysis of H2O to produce hydrogen, which in turn it is used as an alternative source of fuel. For example, 1 mole of hydrogen gas can produce 285.8 kilojoules in the reaction. This is the energy which can be used for something else. What you see on the picture here is just some solar panel harvesting the unlimited supply of energy from the sun, wind power, all right, it's another source of energy. Hydroelectric power, another source of power, hydro and wind power. These are just few examples of renewable. Never delete that. Okay. Please look at problem number 97 and 99 on page 310. I didn't solve an example going with this suggested problem simply because it's a dimensional analysis problem. It's asking about the kilogram of CO2 released into the atmosphere based on, how much of natural gas or combustible fuel is burned. Okay, that marks the end of chapter 7